In this video, we're going to start section 2.2, planes in R3, and we're going to cover 2.2.1, the general form equation of the plane. So let's go ahead and start by reading the goal of this section, and that is to describe a plane in three-dimensional space using either a general equation or a vector equation. So in this video we're going to be doing the general equation, sometimes called the general form equation, and in another video we'll do the vector equation afterwards. So let's have a quick look at this diagram. A plane is a two-dimensional infinite flat surface. So want to be very clear here that these are not boundaries, right? The plane goes on in all directions. It's infinite, so it doesn't have a boundary, it doesn't have an ending part or point or anything like that. Also, something to watch out for is that when we say flat, that does not mean necessarily parallel to the axis, right? Planes may be tilted, right? They may be tilted with respect to the axes, tilted with respect to axes. They might be parallel, but they don't need to be. Okay, and so what else we see in this plane here is a bunch of stuff that we're going to be using in later parts. We see a vector n, which is perpendicular to the plane, which we call a normal vector. We see a point P inside, and we see two other vectors that are parallel to the plane or can be drawn within the plane. So let's go ahead to the general form equation of the plane here. And so let pi be a plane in R3. Pi, so pi, that's not the number, 3.14159, etc., right? That is just a Greek letter. And since we use p for point, we use pi to represent just the name of the plane. So given a point p, which is x0, y0, z0 in pi, and a vector n, abc, that is perpendicular to pi, we're asked to derive the general form equation, or the general equation for pi. And the way that we're going to do that, we're going to start out here by letting q, x, y, z be any point in the plane, any point in pi. So let me go ahead and add point Q here. Doesn't matter where it is. How about there? That means that I can draw a vector PQ between the points, and I can represent the origin maybe somewhere here. And that's a good time to mention. You'll notice that this is just a sketch of a plane. Right? I've not drawn any axes. I've drawn it just nice and flat so that it's easy to draw, easy to sketch. So a lot of the time when we give just diagrams of planes, they're not going to have axes. They're not going to be proper graphs. It'll just be a sketch showing salient information and showing relative positioning of things, right? So I put the origin somewhere. You can just sort of imagine that it is, there is an origin and things are well connected. This would be vector OP, this would be vector OQ, forming a nice tip-to-tail relationship, and here is our perpendicular vector n, right, our normal vector. So we've got our point Q here, we've got our vector PQ, and what do we notice? Well, vector PQ has to be perpendicular to the normal vector if it's in the plane. And if that's the case, you learned in your previous section on vectors that the dot product of those two has to be 0. And we know that with a tip-to-tail relationship, we can say PQ is OQ minus OP. Dotted with n gives us 0. Using the distributive property of the dot product, we can distribute that. So OQ dot n minus OP dot n gives us 0. OQ is the position vector of x, y, z. N is the vector ABC. Minus x0, y0, z0. Dotted with, again, ABC. That has to give me 0. Writing out the dot product, I get AX plus BY plus CZ minus, open a bracket, AX0 plus BY0 plus CZ0 has to give me 0. Now take a look at all this. This is comprised of the normal vector ABC and the point x0, y0, z0. That's given. In other words, everything there is just constant. So what we're going to do is we're going to let D represent this constant. We're going to calculate or collect that all together. So we have a single number D representing that constant, and we end up by being able to write AX plus BY plus CZ plus D equals 0, and that is the general form equation, or the general equation of the plane in R3. Now there's a couple of things that we should just take stock of here. And that vector perpendicular, that vector is called the normal vector. And if you remember from the beginning of the problem, n was a, b, c, and you can actually still see the components of n sitting right there, right? It's n, the normal vector, is apparent in the general form equation. And just another little bit of nomenclature, right? The general form equation, I've been using them interchangeably, is sometimes also called the general equation. The standard equation, you might see the normal equation, the implicit equation. All of these things refer to this same equation here, which represents a plane in three-dimensional